Here we continue to our video 5 on waves and oscillations, and this one is going to be a lot of practice, but it does have one lesson on a new concept that you need to know, and it's usually tested on AP exam. The formula is not given, but this is always asked on AP exam. So this is the formula that shows that velocity depends on the tension in the string. So T stands for tension, so you have T, and divided by the mass of the string per length. And the mass per length has the mass per length constant for each string. So it has letter mu, and it is again mass per length. So the velocity of the string will depend on the square root of the tension over mass per length. So it depends on the tension. And a lot of questions on AP exam ask this conceptual understanding, and they will say, what if we change the mass? What if we change the length? What if we change? And so they want you to understand how velocity and the wavelength will change. And remember that the frequency depends on the source. So if there is a machine that produces that frequency, then that frequency stays the same. That depends on the machine. But the wavelength and the velocity will change because of the tension in the string. So let's look at a few examples and see how we can use this formula to solve problems. Here's the first question we're going to look in this video. A wave whose wavelength is 0.3 meters is traveling down 300-meter long wire whose total mass is 15 kilograms. If the wire under tension of 1000 Newton, what are the speed and frequency of this wire? So we need the speed and the frequency. So to find the speed, we have the velocity is equal to the square root of the tension divided by the mass per length, and I have the tension, which is 1000 newtons, and the mass, they say it's 15 kilogram, and the length is 300 meters. So that gives me 141.42 meters per second. And so I found the speed, but now the frequency. The frequency is going to be the velocity over the wavelength. Velocity is 141.42, and the wavelength is 0.3, and that is equal to 471.4 hertz. Here's another example. What will be the fundamental frequency of a 26 centimeter long organ pipe at 20 degrees Celsius if it is open on both sides or if it is closed on one side? If they give you ever the temperature, then they probably want you not to take the velocity of the sound 340. They want you to calculate it, and there is a formula. So the velocity of the sound is equal to 331.4 plus 0.6 times and the temperature, so that is 20. So the temperature, the velocity of the sound will depend on the temperature. So in this case, you have the velocity of the sound is equal to 343.4 meters per second. So I have to use this velocity unless they don't tell me any velocity, then I will take 340. They also tell you that the organ pipe is 26 centimeters. So, and if it is open on both sides, so if I have the organ pipe open on both sides and the length of it is 0.26 meters, then the wave inside would look like this, and that is 1/2 of the wavelength. So L in this case is equal to 1/2 of the wavelength. Then the wavelength for fundamental frequency. So if it's fundamental frequency, that would be the form of the shape of the wave. So if I times both sides by 2, I get 0.52 meters. So the wavelength is 0.52 meters. And I have to find the fundamental frequency. So now the frequency, in this case, the fundamental, is going to be the velocity over the wavelength. So velocity I found 343.4, and the wavelength I found is 0.52. Now if I enter this into my calculator, I will get 660.4 hertz. This was for when I had both sides open. So now if I have a pipe that is on one side closed and the length of it is still 0.26 meters, then the wave inside would look like this. So in this case, L is only showing you 1/4 of the wavelength. Then the wavelength is equal to 4 times the L, which is 0.26. That gives me 104 meters. And now when I know the wavelength and I know the speed of sound in these conditions, I can find fundamental frequency for a one-side closed pipe. I have again velocity over the wavelength. Velocity is 343.4 and the wavelength is 104, and that will give me 330.2 hertz. Here's another question that is good to look at. We have a sound wave resonates in the tube with 2 open ends. What are the wavelengths of the 3 lowest resonating frequencies generated in the tube? So we have the tube with 2 open ends. So here I have length. The fundamental frequency will give you this shape, and I need to find 3 of them, right? So I have the same length. The next frequency that you would hear is this one with this wavelength, and the next one with the same length, you would see this wavelength. So in each case, I have L is equal to 1/2 of the wavelength. In this case, I have 2/2 of the wavelength. And in this case, I have 3/2 of the wavelength. From here, they ask me to find what are the wavelengths of the 3 lowest resonating frequencies. So the first one would be the wavelength is equal to 2 times L. The next one, the wavelength is equal to L. And the last one, the wavelength is equal to 2/3 L. So my answers are 2L, L, and 2/3 L, which is B. Let's look at this question as well. The lowest frequency in an open pipe is 300 hertz. So that's the fundamental frequency. What are the 3 following frequencies that will resonate in this tube? So an open pipe, that means I have both sides open. And in these conditions, the frequency was equal to 300 hertz. And I'm going to say if this is the length, then the length is equal to 1/2 of the wavelength. And the wavelength is equal to 2 times L. So for the next frequency and for the following frequency, so I don't change the length of my pipe, I just change the frequencies. So for the next one, I'm going to have this wavelength, and for the next one it's gonna be this one. So in this case, again, L is equal to lambda, and in this case, L is equal to 3/2 lambda. So lambda is equal to L, and lambda is equal to 2/3 of L. Also, the velocity is equal to the wavelength times the frequency. The velocity doesn't change, the frequency changes, and the wavelength is changing. So if I had 2L, so for the next one I have 2L was related to 300 hertz. For the next one, my L is 1/2. So if I plug in 1/2 over here to give me the same velocity, my frequency has to be twice as big. So in this case, I will have the frequency equal to 600 hertz. And with the same reasoning, if my wavelength is 1/3 of original one, because it's 2L over 3 now, 2L over 3, then my frequency has to be 3 times bigger. So my frequency from this equation has to be 3 times bigger because my wavelength is 1/3 of the original one. So in this case, if it's 3 times bigger, then that gives me 900 hertz. And I would do the same for the next one, which would be 2 times the wavelength. So for the next one, I would have, so if I do another pipe, because I need 3 new ones. So, and if I do another wavelength, in this case, your L is equal to 2 wavelengths, or the wavelength is equal to 1/2 L. So what you're doing here, you're making 1/4 of the original. Original was 2L, now it's only 1/4 of it. That means your frequency has to be 4 times as big, and 4 times as big as the original gives you 1200 hertz. So you see that the answer is A. Here's another question that I want to look with you at. The lowest frequency in an open pipe is 200 hertz. With the following frequencies, which of the following frequencies will resonate in the tube? So here I have an open tube, and the lowest frequency that resonates would look like this. And so the lowest frequency is 200 hertz. And if this is L, then L is equal to 1/2 of the wavelength, and the wavelength is equal to 2L. So which of the following would resonate? So in the next one, if it's still the same tube, then I would have this frequency or this wavelength resonate. So L is equal to lambda. And if you see the relationship, at first I'm going to write the formula. The velocity depends on the medium. Velocity is equal to the wavelength times the frequency. So when I change, velocity will not change because in certain medium, that velocity stays the same. And I'm going to be changing wavelength and the frequency to adjust, to make different tone of the music, right? Or the different tone of the sound. So in this case, if my wavelength became 1/2 of the one that used to be, my frequency has to be twice as big. So 400 would resonate. So here I have the answer 400 that would resonate. I can look if there is more. So for the next one, I can say, okay, here's the same pipe. And now I'm going to have this wavelength. In this case, my pipe is equal to 3/2 of the wavelength. then the lambda is equal to 2/3 of L. Now I'm going to compare this with the original one. If this is the original one, then this one is 1/3. If this is 1/3, to keep the same velocity, my frequency has to be 3 times as big. So if the original frequency was 200, then this frequency would be 3 times as big, 600 hertz. And this one we said would be 400 hertz. So there is no higher, so 400 and then 600, and then it will be higher and higher. So there's no other choices in my multiple choice answers to choose from. So the only answer I have here is D. Here's another question that we're gonna look at today together at. So I have a uniform string has a mass of m of 0.03 kilogram and a length of 6 meters. So you have the mass is 0.03 kilogram, the length is 6 meters. Tension is maintained in the string by suspending a block of mass 2 kilogram from one end. Find the speed of a transverse wave pulse in this string. So at first I'm going to write all the forces acting on the mass. So I have mg and I have tension. So the force of tension, F net is equal to ma, so the tension minus mg is equal to 0. So the tension is equal to mg and equals to 20 newtons, because the mass of the hanging mass is given 2 kilogram. Then I can find the speed. The velocity is equal to, because it's about tension, so I have the tension over the mass per length for the string, and equals to 20 is the tension, and divided by the mass that is given 0.03 kilogram, and the length is 6 meters. So it will be approximately 62.6 meters per second. And then the time it takes the pulse to travel from the wall to the pulley. So from the wall to the pulley is 5 meters. And if I want to find the time, it is the distance over the average velocity. The velocity I just found, so this is the velocity. And the distance it travels is 5 meters. So 5 meters divided by 62.6 will give me 0.08 seconds. Here's one more question that we're going to look at together. So a spring of constant K equals to 100 newtons per meter hangs at its natural length from the fixed stand. A mass of 3 kilogram is hung on the end of the spring and slowly let down until the spring and mass hang in their new equilibrium position. Find the value of the quantity x in the figure by how much it got stretched. So I'm gonna use again the force of gravity mg and the force of the spring. So I have the force of the spring, because it's equilibrium, minus mg is equal to 0. The net force is equal to 0. So the force of the spring is equal to mg, or kx is equal to mg. So I have x is equal to mg, which is 30, because m is 3 kilogram, divided by k, which is 100, and that gives me 0.3 meters. So the answer for A is 0.3 meters. For the next question, they say the spring is now pulled down an additional distance and released. So it pulled down additional same distance, 0.3, and then released from rest. What is the potential energy of the spring in the spring at this distance. So the potential energy of the spring is equal to 1/2 kx squared, and x in this case, from the equilibrium where it was, is 1/2, k is 100, and x is 0.3 squared. So that will give me 4.5 joules. And then for the next one, find the maximum velocity of the mass as it passes through the new equilibrium that they reached. So it has a new equilibrium. So the velocity of it, this potential energy, is going to go to the kinetic energy. So the kinetic energy of the mass is going to be the maximum mechanical energy that we found, which is 4.5. So I have 1/2 mv maximum squared is equal to 4.5. That means mv squared is equal to 9, and v is going to be equal to 1.7 meters per second, because the mass is 3 kilograms, so I divide both sides by 3, and then take the square root of 3, gives me 1.7. So here I had 4.5 joules, and I have 1.7 meters per second. And how high above the equilibrium will the mass rise? So because the amplitude is 0.3, so it will rise 0.3 meters up and down from the equilibrium. And what is the period of the oscillation? So the period of the mass spring system is equal to 2 pi, and the square root of m over k. So the bigger the mass, the longer time it will take to restore in the original position. So I have 2 pi, and mass is 3, and k is 100. So I will get 1.1 second. Here's the question that I want also to look with you at. A flute is playing with a first harmonic. So the first harmonic is given. The length of the air column is 89.2 centimeters. Find the speed of the wave resonating in the flute. So I have the flute, both sides are open, and the first harmonic looks like this. In this case, I have L, and L is equal to, again, 1/2 of the wavelength. Then the wavelength is equal to 2 times L, which means it's 2 times 0.892. That gives me the wavelength is equal to 1784 meters. And from here, because I know the frequency, I can find the speed is equal to the wavelength times the frequency. So the velocity is equal to the wavelength, which is 1784 times 196. So the velocity is equal to 349.66 meters per second. Look at this question as well. An empty bottle, height 0.2 meters, and the second empty bottle of height 0.4 meters are placed next to each other. One person blows into the tall bottle and one blows into the shorter bottle. What is the difference in the pitch of two sounds? So both bottles are on one side open, so I'm gonna have the taller bottle and the shorter bottle. And in this case, I have this as a standing wave, and in this case, I have this as a standing wave. Let's call this height of the bottle H, and this height of the bottle H. So it's the same as L in our previous problems. So in this case, my H is equal to 1/4 of the wavelength. And in this case, my H is also equal to 1/4 of the wavelength. And let me call a length 1 and wavelength 2. So this one is 4 times the longer H, or taller H, and this one is 4 times the shorter h. And the frequency is the one that you hear. The conditions are the same. It's the same medium, the same air for both of them. So the frequency for the first one is equal to the velocity over 4h, and the frequency of the second one is equal to the velocity over 4h. You can see that this frequency is going to be higher for the fundamental frequency. Let me say sub-zero, so it's fundamental frequency. And this one is going to be lower compared to F2. So the one that has the lower frequency, it has lower pitch. The one that has the higher frequency has higher pitch. And for the next question, they ask you, what would you do to make them sound the same? You would have to fill up with water one of them to make both of them, the air column, the same. So if this air column is the same as this air column, then their pitch is going to be the same and they will produce the same sounds. We have time for a few more questions here. So I have 2 sound waves are traveling through a container of unknown gas. So they're 2 sound waves traveling through the same gas. Wave A has the wavelength of 1.2 meters and wave B has wavelength of 3.6 meters. The velocity of the wave B must be blank the velocity of wave A, because velocity depends on the medium and they travel in the same container. They have the same velocity in the same medium because they are 2 sound waves, and sound waves will travel in the same medium at the same speed. I thought we should look at these tricky questions. So here's another one. 2 sound waves are traveling through a container of unknown gas. Wave A has a wavelength of 1.2 meters, B has 3.6 meters. Their frequency. So the frequency depends on the source, and they have the same velocity, but they have different frequencies in the wavelengths. So the velocity of the A is equal to the wavelength of A and the frequency of A, and the velocity of B is equal to the wavelength of B and the frequency of B. So the frequency of B, so if I solve both sides by, and the velocity is the same. Actually, let's do it this way. A is 1.2 frequency A, and B is 3.6 frequency B. But the velocity for each of them is the same. So A is equal to B. I don't even have to call it A and B because it's the same. So if the velocity is the same, to compensate, your frequency A has to be 3 times the frequency of B to give you the same velocity for both of them. So if this number is 3 times smaller and this time is 3 times bigger, to give the same velocity, your A has to be 3 times B, or B has to be 1/3 of A. I'm gonna stop here for our lesson 5 on waves and oscillations, and there will be some links in the description that you should follow, and you can follow the next one to watch the next video, and I will make the next video on Doppler effect. And thank you for watching this one, and I will see you in the next video.